Hello everyone, welcome to the Spintangle. Today we will be discussing on a very new topic to us, that is canonical ensemble. Canonical ensemble. I think this is not too much new to you because I have discussed it on a lecture on a say the lecture. I think the name of the lecture is ensemble outlines. Okay, in which we have seen, if you are not um, you have not completed that lecture, then you can go to the lecture. Okay, I am giving the link of the lecture. Okay, yes. Canonical ensemble. What is a canonical ensemble? A canonical ensemble in which number of particles, volume and temperature remains constant. Okay, remains constant. This is the general symbol of a microstate in canonical ensemble. Say this is a microstate in VT. It is defined as as these parameters. Say this is number of particles, this is volume, and this is temperature. And in case of ensemble statistics, we take the mental copies of this thing. Okay, this is our original system, and these are the mental copies in VT. Why we take mental copies? Because if we include a change in our original system, then it will be automatically copied to the mental copies. Okay, these are the mental copies. These are what? These are macro state. Okay, this is not, I have told you micro. This is macro state. Okay, this is macro state. So in case of canonical ensemble, a macro state is defined as NVT, n constant. N constant. What does it mean? That the walls of the container are, say this is impermeable or impenetrable. Okay, okay. And in the second term, what we see, that the volume has to remain constant. That is volume constant. This volume constant means say the walls are rigid. Okay, walls are rigid. Now temperature constant means say the walls are temperature constant, means the walls are diathermic. Okay, and the nature of the system is what? These are the four parameters that we have to define before going to the main core topic. Okay, the system should remain in contact with a heat reservoir. Okay, system should remain in contact with heat reservoir. That means what that does means? This means to say this is the system, this is the macro state. Okay, macro state defined as NVT, and it should remain in contact with a heat reservoir. Okay, that means this is the system. I think this is the system, and it should remain in contact with the heat reservoir. That say this is the heat reservoir. I'm doing this thing. Okay, say this is the heat reservoir, or this is called infinite heat bath. Okay, this is infinite heat bath. This is because of the you can easily check this thing out, that the walls of this container is diathermic. That means it can give heat to the infinite heat bath, or it can take heat to infinite from infinite heat bath. So if a sudden increase of temperature happens in the system, that T goes up by some mean, okay, therefore the system will automatically release some heat to cool it down, okay. And if the temperature is lower, that means by any means the temperature of the system goes lower, therefore the system will take heat from the reservoir, okay. This is the function of the infinite heat bath, okay. This is the function of the infinite heat bath, okay. This is the thing that we should encounter in case of canonical ensemble, okay. What is the leading thermodynamic variable in case of this thing, okay. And let me change the ink. Here the leading thermodynamic variable is here, the leading thermodynamic variable is Helmholtz free energy, okay. Helmholtz free energy, that is given by A, okay. Let me reformat the pages, okay. Okay, I think this is okay. Helmholtz free energy is the leading thermodynamic variable. What is given by, that is given by, say A is equals to minus KT ln Q. Okay, what is Q here? Q is called, what is Q here? Q is called single particle partition function. Write this thing out and I will be discussing on this topic, okay. And in case of n particle system, for n particle system, sorry, for n particle system, Q is replaced by Qn, okay. That is, what does this means? This is the n particle, this is called here, Qn is called n particle partition function. Please write these things, I'll be discussing this thing, okay. So this is what we call the canonical ensemble and the leading variable, okay. Now discussing a slight bit, I am discussing the energy. The energy of the system can have any values, okay. The energy of the system can have any values from 0 to infinity. Why this is? Because the system is in contact with a heat reservoir, okay. You have to remember this thing, that 0 to infinity, say this is 0 to infinity, that means you can have, this is ground state energy, say this is ground state energy, you can have first excited state energy, second excited state, third excited state, this is 1 2 3, this is 0 ground state. I am writing this ground state as 0, okay. 1 2 3 so on and so on, and there will be continuous, okay, continuously from, this is the energy, say this is the 0 energy, say here energy is 0, and here up to this thing here will be continuous systems. Okay, continuous, this means E will tends to infinity. Okay, this is the thing that I am aware of. Okay, now, okay, say I am discussing the partition function. Okay, discussion on partition function. Let me write a heading here. Okay, say this is discussion on partition function. Okay, what is a partition function? Okay, let me before moving to the descriptive behavior of the partition function, I am making a model, and you are allowed to make this model if you want to make this thing. Okay, so say this is the energy, this is the energy level. So say this is the energy level E1. In this energy level you have N1 systems. Okay, say this is the energy level E2. In this, say you have N2 N2 systems. Okay, and here is E3, and you have N3 systems, and so on. Say this is, and so on, and here is the energy level. Say this is ER, and you have NR number of states in this, it having this energy. Okay, that means I'm writing this thing out. Just wait. Say there are N1, N2, N3 dot 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 NR number of states are in are sorry, states having E1, E2 dot 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 E are energy levels. Okay, therefore, say this is, I'm writing this thing out, that N1 states having energy E1, N2 states having energy E2, and N3 state NR, say this is NR states having energy ER. Okay, this is the thing. Therefore, our question is, therefore, what is the probability what is the probability, so this is T, that Earth system will be found out in ER energy level. This is our question. Therefore, you know how to find probability. That probability of getting in probability of getting the system is in the, sorry, not I'm Earth system. There will be Earth system. Okay, will be Earth system. The probability of the Earth system having energy ER, it is written as, say, number of systems. I think you know this thing. Number of systems having energy ER by total number of systems in the probability lecture. What we have seen that the probability of having some variable is equals to favorable number of favorable ways by total number of ways. Yes, total ways. Okay, favorable upon SAF upon n. Okay, this is the thing. This is the number of this. In the numerator you have the favorable ways, and in the denominator you have the total ways. Okay, this is the ultimate thing of getting probability from something. Okay, so I am marking this thing. Okay, so the number of system having energy ER is what? Number of system. How many number of systems having energy ER? There are NR number of systems having energy ER. Okay, the total number of system is what? N. This is the total number of system. That the total number of system is what? N is equals to N1 plus N2 plus dot 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 NR. Okay, that's it. This is the probability of having rth state in having energy ER. Okay, this is the ultimate thing. Now we have, this is what? This is the number of particles. This is also the number of particles. Therefore, in case of number of particles, what we have to think about? We have to think about that Boltzmann distribution law. We know by using Boltzmann distribution law, what we can see that NR will be given by NR will be proportional to, say, I'm writing this thing, this is GR e to the power minus beta ER, where beta is equals to what? 1 upon KT. Okay, and N is equals to what? N equals to, say it is will n, this thing will be, what is N here? N is nothing, say this is NR. Okay, and this is NR. So N1 will be what? N1 will be G1 e to the power minus beta E1. N2 will be what? N2 proportional to G2 e to the power minus beta E2. N3 will be what? N3 proportional to G3 e to the power minus beta E3, and so on. Therefore, total number of particles N will be what? I think you can remove this proportionality symbol by introducing an extra constant. Say this is A. Say this is A constant. I will make this thing A. Okay, and you can remove in each and every case. Therefore, each and every case there will be a constant. There will be the same constant A, because the gas or the system has not changed yet. Okay, therefore total number of particles will be given by what? N1 plus N2 plus dot dot dot, say this is NR up to NR. There will be no such energy levels exceeding NR. Okay, therefore what we can see from this thing, that N1, you put this N1 from this formula. Okay, will be A G1 e to the power minus beta E1, plus it will be in the second term N2 will be what? A G2 e to the power minus beta E2, and plus dot 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 A G3 e to the power minus beta E3. Sorry, not this. I am writing the ER writing. Okay. The last system is Earth system. Therefore, I can write it easily, that summation A Gi e to the power minus beta EI, where I ranges from our first system to Earth system. So we have got that NR, we have got NR, and we have got N from this thing. Okay, what is N? N is this. Okay, so N is this thing. Okay, so probability, going back to the probability formula, the probability of having an energy state R in the energy level ER. Okay, that will be equal to nr upon n. We have our nr in our formula, that is gr e to the power minus beta er upon what is our total n is summation a, say this is gi e to the power minus beta ei, where I ranges from 1 to r. Okay, this thing is what this thing is. This is the probability of er. Okay, this is the probability. Here comes our partition function. In the denominator term is called here the partition function. What is partition function? Okay, just wait. Partition function. Partition function is the denominator. Okay, not the denominator, excluding this a factor. Okay, say this is 1, say a equals to 1, excluding this thing. Okay, so our partition function is written as say pf. You can write this thing, partition function, in case of canonical. Okay, in case of canonical, this is called canonical partition function. Okay, is summation gi e to the power minus beta ei. This is the partition function formula. Okay, so why it is called partition function? Why it is called partition function? Okay, say you have, I'm elaborating this example why it is called partition function, why the denominator is called the part. Now the question is, I'm writing this thing out, why the denominator is called the partition function. Why is denominator only called the partition function? Because you can easily see this thing out, that say you have a chocolate, say you have a chocolate. How many chocolate there are? Number of chocolate is what? 1, and you have to divide it among 2 peoples or 3 peoples, say 3 peoples. Therefore what you have to do, the share will be what? That each people, that the total number of chocolate upon the number of peoples. This means each people will have share of 1/3, that the first person, say this is named A, the person A got 1/3, B got 1/3, and C got 1/3. Okay, you can easily see this thing, that the denominator here is the dividing term. It is dividing the total thing. Okay, the total thing, it is dividing. Okay, if you have 4 peoples, then what will be their share? There will be 1/4. This means the denominator is the action making term. Okay, you can easily check this thing out, that this is the action making term. So what does this? That the probability of ER is equals to what we have did, that say it is NR upon N. Here N does what? N makes division. It makes division. So it is called partition. What makes division is called partition. Okay, this is the ultimate thing, that what partition, why it is called partition function, because it makes, say you have a big house and you have to divide this among 4 peoples, then what you should do, you have to make some partitions here. Say this is the compartment A, this is the this is the room of A, or say this is the room of B, and say this is the room of C, and say this is the room of D. A big house is divided by partitions. Okay, this is the thing. So I think if I have understood the concept of partition functions, very few books you can read where partition function has been described with too much elaborate. Okay, so this is the partition function, and we will learn how to write the partition function. Okay, how to write the partition function. So now we are going to the fact that relation between partition function, just wait for a while. Next topic is our what? Relation between partition function and internal energy. Okay. So what is our internal energy? Internal energy is given by U. It is what? It is the average value of the earth state energy. Okay, this is what internal energy is. What, say you have some systems like this, you have some systems, and by averaging the energy of these systems, you may get this internal energy. Okay, this is the internal energy, the average. This is nothing but the average of the total constituent particles energy. Okay, this is the internal energy. So what you have to do, we have did the average value. How to find average value? We have how to find average value. How to find average value of some variable. So this is, I'm writing this thing out. Say if you have a variable x and you have to find the average value of this thing, then what you are supposed to do? Let's say it will be written like this, and I think this has been discussed on the say lecture 3 or 4 in the deviation mean what in the mean deviation lecture. Okay, what was that? The probability of finding the particle and its probability, the value of x and probability of getting x, and here it is the total probability. Okay, this is the thing. Okay, this is, so say summation of this thing and upon this thing. Therefore what does it become? Therefore in case of finding u, what we have to do, that is average of er. This means what? Say average of er and probability of getting er upon total probability. Total probability is what? Total probability is 1, always 1. That means the denominator becomes 1 and the numerator is the surviving term. Okay, er b er. Therefore what we can see, that u becomes summation of er probability of er. Okay, so what is our value, probability of er? We have discussed in the previous topic that what is the value of probability of er. From the previous topic you can easily write this thing as, say this is summation of er. You can easily write this thing as, this is gi e to the power minus beta ei. Here it will be a summation gi e to the power minus beta ei. Therefore you can replace this thing, you can write this thing as er. Okay, you can write this index indices as ER, whatever it is, the summation because I have written the summation over R. Okay, this is the summation over R, the summation over R. That means what we have to do here, this is R. Say now that I'm moving this summation R on the denominator with multiplying this R with the numerator, sorry, with the this means this becomes ER GR e to the power minus beta ER. This is the summation over R, and this is also the summation over R. In the denominator it is GR e to the power minus beta ER. This is the thing. Okay, so what we can write from this thing, you can write this thing as, I am writing a formula for this. Just check this thing out, that I can easily write partial derivative with respect to beta ln here the term summation gr e to the power minus beta er. Check this derivative. Okay, check this derivative, it will become this thing. Okay, check this thing, because ln, you have taken ln, therefore the total term will be in the denominator first, and there will be derivative of this thing. Okay, and there will be derivative of this thing. This with respect to beta, you have to follow this thing up, that you have to differentiate this thing with respect to beta, and here the er will be treated as the constant, and the constant term will be opted out from the bracket. Okay, therefore, and the negative sign, and here also a minus er will come, and that will be doubled up to be positive. Okay, this is the whole thing, that this is U, this is the internal energy. That internal energy becomes minus del beta ln, say this is Q, this is Q. You can easily check this thing, that this is our partition function. This is our partition function. That means partition function is written as Q. This is the ultimate and very important formula to remember. You have to remember this thing for your competitive purpose, and this is too much important for a formula. Okay, this is very important. So where Q is what? Q is equals to summation gr e to the power minus beta er. This is the partition function. Okay, okay, now I am moving to the fact that how to write partition function. Okay, how to write partition function, just wait. Make a heading that how to write partition function. Okay, what is our partition function, how to write this thing? Okay, say our partition function, you know our partition function is given as Q equals to, I am writing this thing before going to the core topic. Okay, gr e to the power minus beta er, or whatever it is, that if summation is on gi, you can write this thing as gi also. Okay, whatever it is, summation, and these are called dummy indices. Okay, these are called dummy indices. The R is called dummy indices. Dummy indices are the indices that can be taken any, and you can write this thing in this place, A, B, C, D, I, J, K, L, whatever it is. Okay. So quantum mechanical partition function is written as quantum mechanical partition function. It will be required in case of Bose-Einstein statistics and Fermi-Dirac statistics, because these are the two statistics which are called quantum statistics. Okay, quantum statistics. Okay, this is quantum mechanical partition function, that's why I have called this thing out. Okay, therefore single particle quantum mechanical, in this thing quantum mechanical partition function, you make a point that single particle partition function single particle partition function, it is written as q1. Okay, this is summation gr e to the power minus beta er, where gr is what, where gr is the degeneracy of the er energy level. This is the single particle partition function. Now for n particle partition function, for n particle partition function, say it is written like this, qn is what, that the partition functions are some kind of multiplicative in nature. Okay, this is q1, say this is for the second particle, say this is q1, this is q1, this is q1, all the particles have partition function q1, and if there are n particles there will be n times, up to n times q1, that will become q1 to the power n. This is for distinguishable particles. Okay, if the particles are quantum mechanical but distinguishable. Okay, this is quite impossible the term, but sometimes in few questions they are mentioned that quantum mechanical distribution and distinguishable particles. Okay, therefore you have to treat this thing out from this. Okay, for indistinguishable particles, for indistinguishable particles, in case of distinguishable to indistinguishable, we know in case of what we have did, this thing we have did in the I think in the Gibbs paradox topic, that in case of going from distinguishable to indistinguishable, what we have to introduce, that a n factorial term in the denominator, that means it will become the qn power n, that this is the distinguishable part. In case of indistinguishable part, there will be n factorial. I have discussed this thing on the Gibbs removal of Gibbs paradox topic. Okay, you can find a lecture named removal of Gibbs paradox. Okay, in this removal of Gibbs paradox, there will be n factorial times, because indistinguishable particles will create less states. Okay, less number of microstates. Therefore we have to divide with a positive number to reduce the number of microstates in case of indistinguishable particles. Okay, okay, now we are going to the classical statistics. For the classical statistics, okay, so for classical statistics we used to write the classical partition function. I just wait for a while. Okay, in the green, I have to write in the green. Just wait. Classical partition function. Okay, so this is classical particle function. In case of classical particle function, for a single particle, so a single particle partition function will be written as single particle partition function. Single particle partition function will be q1 equals to 1 by hf. Okay, f is the degrees of freedom, and two integration will be introduced here, a to the power minus beta e d cube d df q and df p. This is the partition function in case of single particle. We have discussed this formula excluding this term. Okay, in case of classical, that we have calculate the microstates, number of microstates in case of classical mechanics. Okay, in case of classical statistics. Okay, the first integration is over the space and the second integration will be over the momentum. Okay, because this is the formula in the QP space. This is called phase space. Okay, this is the phase space formula, where F is what? Where F is degrees of freedom and E is what? E is the energy. Okay. Okay. This is the thing, I think, for now for indistinguishable particles. This is the formula for distinguishable. Sorry. Just for distinguishable particles. For distinguishable particles, the n particle partition function. This is n particle partition function will be written as q1 power n. And for indistinguishable particles, what do we have to do? Indistinguishable particles, you have to divide this thing by n factorial. Okay, this is q1 power n upon n factorial. Okay, why? To remove the to reduce the number of microstates. Okay, what is this? Okay, so this is over the canonical distribution functions and various formulas related canonical distribution function. You have to remember three things. I am making a conclusion of this thing. Okay, conclusion of this thing. This is say partition function. You have to remember these things. You have to remember partition functions. Single particle partition function is given by q1 and n particle is given by qn. If there are n particles, then what you have to do, that what is qn here? This is nothing but q1 power n in case of distinguishable, and in case of indistinguishable, what is this? It is q1 power n upon n factorial. This is in the case of indistinguishable. Okay, this is 1 2. What is 2 is equals to u is equals to minus. This is the second formula that you have to remember each and every time, that is minus del beta ln q. You have to determine the partition function, and second, what you have to do, you have to differentiate this thing with respect to beta. Beta is what? Beta is 1 upon kt. So remember one formula, that what is, if beta is equals to 1 by kt, then delta beta is equals to what? Is, I think, differentiate this thing 1 upon kt square, and here will be a del t term. Put this thing out here. Okay, this will become minus del, in the place of del beta, what you have to put? Minus 1 by kt square del t. Here it is ln q. Okay, therefore it will become k t square del t. Here it is ln q. Okay, you can remember this formula also, but I prefer to remember advising this thing, okay, to remember. But this is the internal energy formula, and you have to remember one extra formula that is more important in case of this canonical ensemble. This becomes that A is equals to minus kT ln q. What is A is equals to minus kT ln q? Here A is the Helmholtz free energy. This is the most important variable in case of canonical ensemble. Okay, from this, by using this formula and by combining two other formulas that I have given, and there are two important formulas, that TdS equals to du plus P dV minus mu dN. Okay, and the second one formula, G is equals to U plus PV minus TS. Okay, by combining to this formula, you can easily obtain any variable whatever you need. Okay, that is, you can obtain Helmholtz free this enthalpy. This is what? This is H, and U minus Ts is what? This is A. This is this A. Okay, I have given this thing. In the very next lecture, we will be discussing on various conditions like problems. I will be giving some problems, and you have to calculate the partition function for each and every problem. A partition function, and we'll do some important questions, that how to deal with the important questions. Okay, so up to this thing, please share, and you are not giving like as much as I am expecting. Okay, that's why if you have to give like, or otherwise my channel will be in sync. Okay, so thank you for being with us. Increase the number of subscribers, share among your friends.